quicksort has this bad behavior in the worst case. So the question is, why do we use it? Well, the reason why we use it is that in order to get to the worst case, you really have to be unlucky at every step. Okay? Suppose you have a whenever you make a split, let's say one split you're lucky and the other one you're unlucky. Let's see what happens in that case, right? So T of n, so you have unbalanced split, so we have T of n plus T of, so one partition is 1, the other partition has n minus 1. Okay? So I don't know why I added n twice, so that's probably, that's just a typo. So n plus T1 plus Tn minus 1. So T1, well, you don't have to sort this one partition, so it's n plus 1. And let's say when you do the, when you try to quicksort an array of n minus 1 elements, you get lucky and you get balanced split, right? So that means you'll have 2 times T of n minus 1 by 2, right? So, and then also the partition cost for partitioning an array of size n minus 1 is n minus 1. So you add this n plus 1 plus n minus 1 plus 2t, so you'll get 2n plus 2t times n minus 1 by 2. Right? And once again, if you apply the master theorem, it will tell you it's an n log n algorithm. Right? So if you get lucky every other time, you're okay. What happens if you don't get lucky, but at least the way you split them is not a disaster, right? So let's say you divide them in the ratio 1 to 3, not 1 to n, right? 1 to 3. So 0.25n on, so n1 becomes 0.25n, and n2 becomes 0.75n, right? And now what you can say is that, okay, how do I solve this? One simple way is to say, okay, I'm only computing, I want to establish an upper bound for running time, right? So I can always approximate to get an upper bound. So instead of 0.25n, I can say, well, T of 0.25n is less than or equal to T of 0.75n, so I can combine these two terms into 2T of 0.75n. And then once again, if you apply the master theorem, it will tell you it's still O of n log n. Okay? So what it tells you is that, yes, there exists a worst case, but unless you reach that worst case, very often the algorithm ends up being O of n log n. Okay? So now the question you can ask is, can you think of a case where you will always hit the worst case?
The one when you partition it such that it is one.
But can you think of a concrete case where you will always end up with a 1 and n minus 1 split? So the question cannot be answered without saying, picking your pivot selection algorithm. Okay? So let's say you always pick the first element. Okay? Now, can you think of an input on which you'll get the worst case behavior? Sorted from low to high, right? So the list is sorted from low to high, and you always pick the first element as a pivot. Well, then the first partition will just have that one element, and the everything else will be in the second one, right? And now you apply recursively. Once again, the elements 2 through n are still sorted, and you pick the pivot as the first element. In that, again, you'll end up with a 1 n minus 1 partition, right? So if you do the last element, if you always pick the last element as the pivot, well, then you will have worst case behavior if the list is sorted in descending order, right? So once again, so the point is that if you have a fixed way of picking a pivot, then it's fairly, you can easily run into these really unlucky or worst case behaviors, right? So this is why quicksort should be always used with a random pivot selection. So now, let's go through the average case analysis of quicksort, which is actually quite interesting. Okay? So what is the average case? So the average case basically says that, okay, I'm going to end up with some k number of elements on the left half and n minus k elements on the right half. Okay? If I consider over all possible ways of partitioning, then I can take the average over all those possible cases, and that would give me the average case performance of quicksort. Right? So this is what this formula represents. So you have TF, you are trying to quicksort an array of size n. You have the partition, which always takes order n time, and then you have two subproblems, right? So you can either run with T1, right? Right, so these represent all possible ways the partition can result in subproblems, right? These are all the ways subproblems. And then to analyze the average case, what you can say is, let me consider the cost of each of these, right? And take the average, right? So we do 1 by n of the summation of all of those elements, right? So that is what this thing represents, right? So we have this summation. Okay? So the question is, okay, how do we solve this recurrence, right? So of course, master theorem is not going to help you, right? Master theorem doesn't deal with summations on the right-hand side, right? So we need some other technique to do this. Okay, so we can use approximations, right? So one thing we could do is, so let's just jumping ahead. So I told you that when we have very complex recurrence relations, what we do is we try to guess and verify by induction, right? So what we're going to do is we're going to say, okay, I'm going to guess that this, right, T of n equals some c times, right? I'm going to guess that value, and then I'm going to try to verify that. Okay? In order to do that, I need to show that Cn log n, right, which is the left-hand side, should be greater, less than or equal to Now you can see that when you add this, right, you have T1 through Tn minus 1 and T1 through Tn minus 1, right? So this is nothing but we need to show that is less than n plus 2 times sigma and 1 Tf5, right? So we don't have two terms. Yeah. Oh yeah. I'm sorry. Yeah. Good catch. So catch me whenever I make mistakes like this. So we can say, okay, so what we are going to do is we are going to substitute our guess on the right hand side, and we want to see that the bound works, right? So we want to say, okay, so we want to ask, what is the summation
C times I log n.
right? So T of I, we are going to substitute our guess on the right hand side, and we check, are we able to still establish a bound? Okay? Okay, so now, well, how do we sum I log I? It's not something that we know how to do, right? So we can try to use approximation and then say this is less than or equal to n plus 2 by n okay? So what we are doing here is we are saying instead of log I, I'm going to replace log I with log n, right? Log n is of course greater than or equal to log I, right? So if I replace log I with log n, then I will get a value that's a summation that's strictly greater, right? So I can actually say, I don't have to say less than or equal to, it's less than, but let's keep it that way. And once this, if I replace it by log n, it's no longer dependent on I, so I can move it outside the summation, right? So now I have a simple summation, and log n has come outside, right?
There should be a C too.
The 2C log n.
Right, right. So 2c log n, right? So unfortunately, this is not going to work because that's going to be a
And
n square log n term, right? So this will become n plus 2c by n log n times n square type of thing. And you can, of course, cross that out with this. But unfortunately, you end up with,
it is bigger
something bigger than
Cn log.
Cn log n, right? Okay, so let me write it more clearly so you can see what's going on. Right, so let me erase this and just write it over there where there's more space. So we have n plus 2c divided by n times log n times n squared, right? So this is going to become something like n squared, right? So we can cancel off this exponent with this. So we'll have n plus 2c, this n, I'll move it over there, log n. So, so what we need to do is we ended up with, so what we needed to do is we needed to establish an upper bound, right? So if we substitute the right-hand side, right? So that should give us a value that is actually less than, right? So if we substitute the right-hand side, we should come up with a bound that's less than our upper bound guess, right? But what we get is n plus 2cn log n, right? So we have this n log n plus something added, right? So it's clear that our proof failed because we wanted to say that the right-hand side is, the upper bound on the right-hand side is Cn log n, but in fact we get Cn log n plus n. So this is not going to work. So we need to do, the reason why it didn't work is because we did a very crude approximation here, right? We replaced log I by log n, okay? So that's, didn't work. So what can we do? So we can, do various things, but I'm going to tell you one nice trick which uses integration, right? Because you know, when you do integral, right, in calculus, you know that integral is simply
Summation.
doing a summation, right? So this summation I log I, right, looks like integral of x log x, right? So we can actually draw a picture and see what the integral value is, right? So let's say 1 right? So at 1, right? So the this term is going to be essentially 0 because log 1 is 0, right? At 2, you have 2 times log 2, right? This is 2 log 2. And 3 log 3. You know, ignore whether the scale is right and so on, right? I can't think about exactly whether the scale is right, okay? So the discrete sum that we are talking about is the area under these, right? Now, the integral is calculating continuous sum. So at x equal to 1, the continuous function is going to be there. At x equal to 2, it's going to be here, and so on, right? So the integral, again, I guess it's going to be slightly more than linear, right? Growing slightly faster than linear. So what you can see is that the area under the x log x curve is
Upper bound.
is slightly larger than the discrete sum, right? By this shaded region, right? So if you are looking for upper bound, well, we can use the integral value, right, instead of the summation, okay? So if we apply the integral, right, then you can verify that the integral of this is that, okay? And then once you supply that summation, then you can, you know, you'll be able to go back and substitute it, and then convince yourself that in fact it works correctly. Okay, so I'll finish this up. Yeah, we'll stop here, and I'll finish up how this upper bound allows us to prove the result. Okay? Yeah.
Limit n, right? From n equal to n minus 1 to n.
Correct. Right. So yeah, all those car edge cases you have to think about very carefully. I just want to give you why this integral is related to the discrete sum, right? So I don't want to go through all of the specifics of whether we got the boundary conditions right, okay? Which takes time and somewhat tedious, but once you get the basic idea of why the integral works, then I think the rest is relatively easy.